Welcome! I am Karen McFarland, the punk rock professor, and I am here to give you clear and concise tools to help you crush chemistry. We're going to be talking about Lewis dot structures today. Now, specifically, instead of neutral molecules like we did in another video, this is for ions. So here's a couple examples that we're going to be looking at. Make sure you have your periodic table handy so we can figure out how many valence electrons we're working with here. All right, so let's start out with NH4+, this ammonium ion. And one of the first things we always want to start out thinking about is, what is the general structure of this molecule going to be? What is the central atom? What is the configuration of the other atoms around that central atom? Now, for something like a molecule such as NH4+, an ion, NH4+, that has hydrogens around it, it makes our lives way easier. Hydrogen can only be on the outside. It can never be a central atom, so we don't have to worry about that too much. We know it's got to be that nitrogen. Otherwise, we do want to think about electronegativity, but here, our life is made a little bit more simple. All right, so we put that nitrogen in the center, and we're going to create single bonds for all of the atoms around that central atom. So this is our starting point. We'll put those hydrogens around the nitrogen. Okay, now we keep in mind this is an ion. So this is when we get a little bit different from how we dealt with neutral molecules. So we need to put brackets around this structure and put what the charge is on this ion. So the way we do that, there's our brackets and there's our plus charge. This has been given to us here in the formula. That's how we know it's there. And it is important to have those brackets and that charge around that ion. If we leave it off, we do not have a fully correct Lewis dot structure, because that's going to tell us how many electrons are involved in the bonding there. Okay, so now let's do that step where we add up all the valence electrons that are involved in the bonding and see if we need to add any more electrons that we might be missing, etc. Okay, so now this is where we do the little tally over here, which is what I always do when I'm doing Lewis dot structures. I count up the valence electrons for each atom in the whole molecule or ion. Okay, so let's look at our nitrogen. So we've got one nitrogen, and I'll multiply that by however many valence electrons we have. Okay, so in the case of nitrogen, we look on the periodic table and it's group 5A, so we have 5 valence electrons. Okay, so the nitrogen, I guess what I meant to put is equals. 1 times 5 equals 5. All right. And then we look at the hydrogens. Okay, so if we tally up all the electrons that the hydrogens are contributing to the whole ion, there are 4 hydrogens. Each of them is contributing 1 electron. So there's our 4 electrons there. Okay, now we need to take into account that this whole thing is positively charged. Okay, so while we do have, if we add these up, we have 9 electrons that are being contributed from all of these atoms. Overall, the structure is positively charged. So that means it has lost 1 of those electrons. So we are going to subtract an electron from that total number of electrons. That gives us 8 electrons. Okay, so this is due to the positive charge that we have on that ammonium ion. Okay, if it was +2, we would subtract 2 electrons. Okay, so the number that we are removing, that is going to be equal to the overall charge on that molecule if it's positively charged. Okay, so that means we have a total of 8 electrons to work with on this ion. And if we now consider, we go back to this skeleton structure that we put together at the beginning, add up all those electrons. Okay, so each one of these bonds, these are single bonds, each one has a pair of electrons, 2 electrons for each of these. So there's 2, 4, 6, 8. Lo and behold, we have 8 electrons that are part of, these are valence electrons that are part of bonding, and by virtue of having all single bonds around the nitrogen, we're done, okay? But we do want to double check and make sure all of those atoms have their octet in the case of most atoms, or in the case of, here's one of our exceptions, hydrogen, it only has 2 electrons. Hydrogen can only ever have at the most 2 electrons. That's all it can handle. It's one of our exceptions. Okay, so when we look at these hydrogens, they're all good. They only have their 2 electrons. We look at our nitrogen, 2, 4, 6, 8. It's got its octet. So we are done. This is a full and complete Lewis dot structure of NH4+. Okay, so now let's look at our other example. Here we now have this phosphorus hexa chloride ion, negatively charged ion. All right. So once again, we take a look at the ion here and we decide what's our central atom. And we build single bonds around it. And then we figure out what's the total number of electrons that we have for this ion, for this whole molecular ion. And then whether or not we need to maybe create double bonds or whatever might be happening, okay? But I do always start out with creating the structure. Okay. So the very first atom in a formula, usually the central atom, but you can't always count on that. So I always do think about which is the most electronegative, which is the least electronegative, and we go with the central atom is going to very consistently always be the least electronegative, okay? The most electronegative atoms will be on the periphery of the molecule. They will be on the outside because then they can more effectively draw electron density towards themselves when they don't have to share as many electrons. Okay, so we see that we've got the less electronegative phosphorus will be in the center, and we have 6 chlorides around it. Okay, so we need to squeeze in 6 chlorides. All right, so we already know that this phosphorus must be expanding its octet. That is something that phosphorus can do. Once we're in the 3rd row on the periodic table, those atoms, those nonmetals, are able to expand their octet beyond 8. They can have 12 electrons, they can have 10 electrons. We saw that example in the other video. So this is not shocking. We don't have to worry about it. And the great thing is we were told this is the formula. So we know that this phosphorus is going to have 6 chlorides around it. Okay, so we have a starting point in terms of the bonds. Now we need to remember, this is an ion, so we got to put those brackets around it and tell everyone what is the overall charge. It's -1. Okay, that was given to us in the original formula. Okay, so now let's do our valence electron tally. We'll start with that phosphorus, and we've got just one of them. So 1 times, and now we look at our periodic table. We see it's group 5A, 5 valence electrons. Not shocking, okay? Our last example was nitrogen, and phosphorus is right below nitrogen. So they should have the same number of valence electrons. That is consistent on our periodic table. Okay, so we're gonna have 5 electrons here contributed from the phosphorus, and that gives us a total of 5. And then in terms of the chlorines, all right, we have 6 of them now. And each of them, again, look at our periodic table. We see it's in group 7 valence electrons for each one of those. Okay, so 6 times 7, and we have a total of 42 electrons coming in from all those chlorines. Okay, so now we can add all these up. We haven't looked at the charge yet or what to do there, but we're going to add all of these up. So we have 42 and 5, so that gives us 47 electrons. But now let's take into account that we have a negatively charged ion here. Negatively charged overall means that there's more negative charge. There must be an extra electron that is contributing to that extra negative charge. Okay, so that means we need to add in 1 electron. Okay, again, this is due to the negative charge on this ion. All right, so we're going to add in that electron. That gives us 48 electrons total to work with. All right, so at this point, we have used 2, 4, 6, 8, 10, 12 of those 48 electrons total, 48 valence electrons. All right, we've used 12 of them. And so now we're going to complete as much as we can, and we'll see what happens here. We're going to put the rest of those electrons around on these periphery atoms, on these chlorines. Okay, so there's our 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48. All right, so if we now double check for all of our octets, or in the case of phosphorus, expanded octet, we see that phosphorus has 12, that's okay. And each of these chlorine atoms, boom, boom, boom. We look around, octets across the board. Everybody's happy. So this is looking good. All right. So we have completed our Lewis dot structure for the PCl6 anion, and we can feel confident that this is correct. All right. So good job. Now for a bonus track, check out my t-shirt. This is the Atom Age. This is a fantastic band from the Bay Area. They are so much fun to see live. You will just love them. So I'm going to attach a link to a really cool video that they have made, Walk Through Walls. Super fun. Their energy is fantastic. And I will say, you have to be a pretty good band to get a sticker on my gig box that I take to shows when I play. And check it out. They made it. Super fun. All right. Well, thank you so much. If this was helpful, please subscribe. It helps me keep these videos rolling. So thank you, and I'll catch you later.